On the far side of the moon, China found something humans had only ever managed to produce in a laboratory. A structure that requires precision technology to exist. Controlled temperature, exact catalysts, conditions that don't occur in nature. And on the moon, it appeared on its own. A team from Jilin University published the finding in Nanoletters in January 2026. They call them single-walled carbon nanotubes, the most structurally delicate objects chemistry has ever produced. And the first question scientists asked wasn't how they formed. It was, why has nobody ever found these anywhere else in the universe? Here's what this video is going to answer. What single-walled carbon nanotubes actually are, and why their existence on the moon breaks what we thought was possible, what natural mechanism produced them on the far side and what that reveals about that hemisphere's history, and the question that connects everything. If the moon can build structures we only make in labs, what else is it producing out there that we haven't found yet? Stay until the end. The last answer opens a door that astrobiologists are taking seriously. The far side of the moon never faces Earth. Same reason we always see the same face, synchronous rotation. The opposite hemisphere is permanently hidden from any observer on our planet. No ground telescope can see it. No radio signal can reach anything that lands there without a dedicated relay satellite parked in a specific orbit above it. This isn't a minor technical inconvenience. It's why no country attempted a far-side landing for 6 decades after the first lunar missions. The communication problem alone required China to launch a relay satellite, Kuekiao, specifically to make Chang'e 4's 2019 landing possible. It was the first soft landing on the far side in the history of spaceflight. Until 2019, no country had ever landed on that hemisphere. Until 2024, no country had ever brought samples back from it. On June 1, 2024, Chang'e 6 landed in the Apollo Basin, inside the South Pole Aitken Basin, the moon's oldest, deepest, and largest impact crater, 2,500 kilometers across. It used a drill and a scoop to extract 1,935.3 grams of soil and subsurface rock. On June 25th, the return capsule landed in Inner Mongolia. Those 1,935 grams reached the labs at Jilin University. When researchers pointed high-resolution microscopy at the micrometeorite impact scars inside the lunar soil particles, they found something that wasn't in any lunar geology textbook. But the nanotubes weren't the only anomaly. The same samples contain another finding that scientists still can't fully explain. A single-walled carbon nanotube is a sheet of graphene, a single atom thick, rolled into a perfect cylinder. Diameter, 1 to 2 nanometers. A nanometer is 1/1,000,000th of a millimeter. For context, a human hair is about 80,000 nanometers wide. A carbon nanotube fits inside a human hair 40,000 times over. The tensile strength of that tube is 100 times greater than steel of equivalent weight. Think about that. The same mass, 100 times stronger. It conducts electricity better than copper. It conducts heat better than diamond. It's lightweight, flexible, and chemically stable in extreme environments. Scientists have been trying to figure out how to mass-produce single-walled carbon nanotubes for decades because the applications are staggering. Faster transistors, stronger structural composites, targeted drug delivery systems that can navigate inside the human body, ultra-efficient solar cells, sensors that can detect individual molecules. The reason they haven't been mass-produced yet is that making them reliably requires extraordinarily controlled conditions, and even then, yields are inconsistent. The moon has been doing it consistently for billions of years, and until January 2026, it was believed they could only be manufactured under very specific artificial conditions, controlled temperatures, metal catalysts prepared in a lab, inert gas atmospheres. The structural complexity of those single-atom-thick cylinders was considered impossible to achieve through spontaneous natural phenomena. Multi-walled carbon nanotubes, thicker, simpler versions, were known to occur in nature. They show up in coal, in ice, in fire ash after rapid cooling. But single-walled ones, the most delicate, the most useful, the technically most complex, had never been found outside a laboratory, until now. And the problem wasn't just that they existed. It was what their existence reveals about what's been happening on the far side. For decades, the standard model of the moon described its surface as a geologically dead environment. No active volcanoes for billions of years. No atmosphere. No liquid water. A place where things slowly break down from solar radiation and micrometeorite impacts. Not a place where complex structures get built. The nanotubes prove that model is incomplete. The Jilin team identified the formation mechanism in their nano letters paper. When a micrometeorite strikes the lunar surface at high velocity, typically between 20 and 70 kilometers per second, it instantly vaporizes carbon from the solar wind and from the meteorite itself. That carbon gas, cooling rapidly onto iron particles in the lunar soil, undergoes a catalytic reaction. The iron acts as a mold. Carbon deposits around the iron core in ordered layers. And if the temperature and composition are exactly right, if the cooling is fast enough and the catalyst has the right size and composition, the result isn't amorphous soot. It's a perfect single-walled tube. The moon has been doing this for billions of years. No human intervention, no lab equipment, just micrometeoritos, iron, and solar wind. Get this, the far side has more of it than the near side. Chang'e 6 samples show more pronounced defects in the carbon structures than Apollo, or Chang'e 5 samples from the near side. Those defects are the signature of a more intense micrometeorite bombardment, consistent with what models predict for the hemisphere that has neither Earth's gravitational shadow nor Earth's presence on its horizon as a shield. The far side is a natural carbon nanotube factory, and it's been running for eons without us knowing. But that's not even the wild part. The same Chang'e 6 samples also contain graphitic carbon, graphene in partially ordered forms, whose presence on the far side doesn't fit cleanly with existing models of lunar carbon flow. Researchers found nanotubes and graphite in the same soil particles, often in the same impact scars, suggesting both processes, nanotube formation and graphite formation, are products of the same high-energy mechanism. And that mechanism has an implication astrobiologists aren't dismissing. Single-walled carbon nanotubes are organic structures, not in the sense that they imply life, but in the sense that they're carbon molecules with precise architecture. The same type of architecture that appears in prebiotic compounds. The molecules that, in early Earth, are considered precursors to the basic building blocks of life. There's nothing in the data suggesting life on the far side of the moon. The nanotubes are inorganic by formation, but their presence proves the moon can synthesize complex carbon molecular structures from high-energy impacts. The same type of process proposed to explain how complex organic compounds reached primitive Earth via comets and meteorites. Turns out the moon isn't just a geological record of the solar system's past. It's an active laboratory of high-energy chemistry, and we've only ever had access to data from one of its hemispheres for 50 years. This converges on something that reframes what it means to explore the moon at all. For decades, the question about the far side was, how different is it from the near side? The standard answer was, more craters, thicker crust, fewer volcanoes. Different in scale, not in kind. The Chang'e 6 samples say something different. The far side has a different carbon composition, a more intense impact history, less water in the mantle, and molecular structures that had never been found in any previous lunar sample. Not Apollo, not Luna, not Chang'e 5. It's not that the far side is more of the same. It's a different kind of moon. That distinction matters beyond geology. If the two hemispheres have different carbon chemistries, different bombardment intensities, different mineral compositions, then 50 years of lunar science built on Apollo samples from the near side is at minimum incomplete. We've been studying one side of a two-sided story, and when Artemis IV lands at the South Pole in 2028, it'll arrive at the transition zone between the two hemispheres. What they find there, if they carry the right instruments, if they analyze the carbon, if they look for the right structures, could change how we understand what chemical processes are possible on rocky surfaces under high-energy bombardment. Not just on the moon, on any rocky body in the solar system. The question I keep coming back to, if the moon can build single-walled carbon nanotubes using micrometeoritos, iron and solar wind, no lab, no intervention for billions of years, what else is nature constructing in places we haven't sampled yet? Drop what you think below. And if this video changed how you see the moon, subscribe. Next week, Artemis IV is planning to land at the South Pole in 2028, exactly in the transition zone between the two hemispheres. What they might find there isn't just ice anymore.